So, welcome to another 4820 lecture after a small break. As usual, let's just start by reminding ourselves what we talked about the previous lecture, where we left off. So last time we talked, we sort of wrapped up what we had to say about training classifiers, and this example of supervised learning from labeled data. So last time we talked about how to evaluate classifiers after we have applied them to gold test data. And then we moved on to talk to sort of another family of machine learning methods that also deal with classes or categories or groups of objects in our data, but this time not using sort of this approach of supervised learning where we're given labeled examples of the classes that we want to predict. Instead, we're just given the data, and then by defining what are to be our features, the feature functions for describing and representing our data, and some similarity metric for measuring the similarity of two objects based on these features. A clustering algorithm is to just by itself come up with a hypothesis about classes or groups that exists in the data. So it's in a sense even more automatic than these supervised classifiers are. So we talked about at the previous lecture that there are sort of two broad approaches to perform clustering. So one are these so-called flat clustering methods. We talked about k-means at the previous lecture, which is maybe the most well-known, most important instance of flat clustering algorithms. And today it will probably be clearer why we call that algorithm a flat clustering algorithm, because today we'll turn to talk about the second sort of main approach of clustering methods, known as hierarchical clustering methods. So these methods, in contrast to the flat clustering methods, they don't just define sort of a partition of the data, a set of groups in the data. They create sort of what we can think of as nested partitions. So sort of a tree structured clustering. It will be clearer later once we sort of visualize this and go into the details. But that's so hierarchical clustering is the first part of today's lecture. So again, there are two sort of sub types of hierarchical clustering methods. It's the so-called top-down methods and bottom-up methods. We'll spend most of our time talking about the so-called bottom-up or agglomerative clustering methods. And then we'll mention top-down methods towards the end. But this is sort of the first half before the break today, roughly. And then after we wrap up talking about clustering, Stefan will take over. And we'll start today with giving you a crash course on probability theory before possibly, if there's time, moving on to language modeling, but Stefan is shaking his head, so probably not. The clustering will roughly be the first half, roughly. But probably just probability theory today, not moving on to language modeling. Okay, so let's just get started with hierarchical clustering then. And we'll start with this first family of methods known as the bottom-up approaches, or the agglomerative approaches, which sounds much more scientific and fancy, but mean the same thing. So that we here see what is meant to be sort of a formal description of how bottom-up clustering works. But trying to show this sort of in formal terms is possibly just more confusing than enlightening, because it's actually a very simple concept, and trying to formalize it might make it seem more obscure than it really is. So the way bottom-up clustering works is that it starts by considering all the objects that we want to cluster as defining their own singleton cluster. So every object defines a cluster of its own. That's our starting point. And then we need to have some kind of similarity measure for measuring the similarity of two clusters. And in each step, the algorithm will iteratively then merge the two clusters that it finds to be most similar. So that will be a new cluster. Then again, it will try to find what are the two clusters that are most similar, and then merge those two, and then iteratively continue to merge clusters until finally there's only one big cluster comprising all the objects in our collection, which will correspond to the root node in this tree structure that these merges give rise to. So each merge operation that we perform can be seen to yield a branch in the tree, sort of building the tree from the bottom and up. Okay, so the most important thing to note here is that there's sort of one important parameter to the algorithm in addition to the objects themselves, the objects that we want to cluster, the object collection for which we want to try to discover these groups within the data. In addition to that, it's the similarity measure itself that we want to use for measuring the similarity of two clusters. And depending on what similarity measure we plug in here, we will end up having possibly a very different set of clusters in the end. So this structure you see here is something called a dendrogram. Basically a binary tree structure, which is typically used to visualize the result of applying sort of such a bottom-up or agglomerative clustering method. So along the x-axis here, we have the objects to be clustered, and then the y-axis shows the similarity level at which a merge occurs. So the coordinate at the y-axis shows the value of the similarity measure that we use for measuring the similarity between two clusters. So at the beginning, right, we have our collection of data points, of objects, and then we start by finding which of these two clusters, these two singleton clusters, are the most similar. So in this case, that turned out to be B and D, and we see that this is the first merge that has been performed. And we see that because it has the highest similarity value, right? So here we might assume that we've used the dot product, for example, as our similarity measure for the individual objects that we compare. We'll get back to the details of how the actual similarity scores are computed here. But at least let's assume that a higher score, so further down on the y-axis here, means more similar. So this is our first merge. Then we merged G and E. Then we merged this new cluster of B and D together with H, and so on, until we reach the top where we have sort of a single root node, including all the objects in our collection. Okay, so this is just having this structure in mind is just helpful to for thinking about what is the end result of applying bottom-up clustering. Okay, so we'll get back to looking at these diagrams a bit later, but first we'll talk a bit about the similarity measures. So far we've talked about how to measure the similarity between individual points, right, using the dot product or the Euclidean distance or what have you, and also the distance between a single point and a class, like we did when we applied our classifiers. So for example, by representing a class as a centroid and then just using the dot product again for computing the distance between an object and a class. What we'll need to do now is to look at ways to define the similarity between two classes. That's something we haven't done yet. Because now in each step of this bottom-up clustering method, we will need to pick out what two clusters are the most similar ones. Each cluster might contain several objects. We need a way to quantify what that means for two collections of objects, two clusters of objects to be similar. And we'll be quickly going through the 4 sort of main similarity measures that are typically used when performing agglomerative clustering, bottom-up clustering. These are known as so-called linkage criterions. Single-linkage, complete-linkage, average-linkage, and centroid-linkage are the names of these 4 similarity measures that we'll look at. And so just to be clear, the role that these similarity measures have in our algorithm is so the algorithm that we presented just a couple of slides ago was sort of just the skeleton of how the general approach of bottom-up clustering works. But then the actual work here is done by these linkage criterions that we can plug in as this similarity measure, this parameter to the general method. And the linkage criterion will determine in each step of the iteration what clusters to merge. Okay, so let's start with one called single-linkage. So we have 2 circles here representing 2 clusters. So we have one cluster with the objects A and C, and then we have another cluster with the objects B and D and E. Okay, now we want to for different such linkage criterions, different such similarity measures, see how we can define how these 2 clusters are similar. And with the single linkage measure, what we do is that we just define the similarity, or alternatively the distance between 2 clusters to correspond to the minimum distance that is seen between any of the members of the 2 clusters. So this is based on this by now familiar idea of nearest neighbor relations. So in this case, we see that of the set of points in the 2 clusters, C and E are the 2 points that are closest. So we'll say that the distance of C and E, that's the distance between these two clusters. And one nice property of the single linkage measure is that it's what is sometimes called best merge persistence. So what that means is if we know that a given cluster has its nearest neighbor in some other cluster X, and we merge that cluster X with some other cluster Y, we know that the closest cluster for this initial cluster will still be this merged cluster with X as a component, because these nearest neighbor relations sort of persist after a merge. And that means that we can compute the clustering very efficiently, because we'll know after we've merged the cluster, we automatically know what is the closest cluster to this merged cluster. But it also has some less desirable properties. It has this so-called chaining effect that has a tendency for the clusters that it produces or discovers, or however you want to call it, to be sort of a bit straggly or stretched out. So it will typically find sort of more elongated clusters. And there's another measure called complete-linkage, which does not have this effect of producing these sort of strangly stretched out clusters, which is called complete linkage. So here it takes sort of the opposite approach of the single linkage criterion. Instead of defining the distance between the 2 clusters as the distance between the 2 closest points, the 2 nearest neighbors of the 2 clusters, it defines the distance to be to correspond to the distance between the points that are farthest away from each other. And in a sense, this amounts to sort of choosing the clusters to merge that will result in a new cluster that has the smallest diameter. It's sort of the intuition here. We'll also give a have a preference for more compact clusters with smaller diameters. One potentially negative effect of complete linkage is that it's more sensitive to outliers in our data sets, objects that are in the periphery compared to the other objects in our collection. And it does not have this nice property of being best merge persistent that we talked about for single linkage. So after performing a merge, we would again need to determine sort of from scratch what is the best candidate for this merge cluster in terms of finding another cluster to merge it with. Okay, average linkage is a third measure. This is typically regarded as sort of the most robust, sort of out of the box in general of these similarity measures that we'll discuss, and typically regarded as what should be considered sort of the default clustering, the default criterion, if you don't have any other good reasons for choosing one of the others. So what we do in average linkage or group average clustering, which is also called, is we compute the pairwise similarities between all the points in the union of the merged cluster. So we can think that we here merge, we have all the points A, B, C, D, E in one and the same cluster, and we compute all the pairwise similarities within this cluster, excluding self-similarities. And then that defines, we take the average, and that defines the similarity of the two clusters. This can be regarded as sort of a mix between single linkage and complete linkage, sort of a compromise here, but also makes it more robust to outliers. And one reason for excluding self-similarities is to not sort of penalize large clusters, which would have fewer self-similarities compared to the overall number of pairwise similarities in the score. Right. And for those interested in the details, if you see in the book, there's by taking advantage of this property that we use the dot product as our similarity measure for comparing the individual objects, and working with normalized feature vectors, there are ways to compute this score very efficiently. But this is sort of so far, when we talked about linkage criterion so far, the only place where we sort of explicitly said that we're working with vector representations. So you have talked about that we could use the dot product, for example, for computing these the similarities between the individual objects in our clusters. But for single linkage and complete linkage, that measure in itself is sort of agnostic to our representation. If you go back to complete linkage, so the measure we use here for comparing A and B, or all the other points within the clusters here, could be sort of any similarity measure that we think is useful. It wouldn't have to be a measure that relies on a vector-based representation of our data. Okay, so that's just worth bearing in mind that this is actually sort of more general than it's not inherently tied to this vector-based representation of our data. Okay, so the final measure is centroid linkage, which would maybe, I don't know, seem like the most intuitive, straightforward way to define the similarity between two classes, given that we've worked with the Rockwell classifier and k-means clustering previously and seen how that's an effective way of representing classes, computing a centroid vector, a mean. So that would mean we wouldn't have to compare all these to compute all these pairwise similarities. We just look at the centroids. So the similarity of two clusters would correspond to the similarity of the cluster centroids. And this is actually computing this score would be equivalent to computing the average pairwise similarity between all the individual objects in the two clusters. And so while this seems like sort of a very straightforward and intuitive way of computing the similarity of two classes or two clusters, it has some undesirable properties attached to it. So one is that it does not have this property of being best merge persistent, but that also held for complete linkage and average linkage. But worse, it's non-monotonic and subject to what we call inversions. What that means is that the similarity of the two clusters that we choose to merge in each step can actually increase from one iteration to the next. So this is a whole lot easier to explain and understand if we visualize it. So let's first try to explain what we mean by the notion of monotonicity in this context. So sort of a fundamental assumption when we do clustering is that our clusters, is that a smaller cluster is more coherent than a large cluster in terms of its internal average, the internal pairwise similarities of the members. We expect sort of small clusters to be tighter than a large cluster. You would expect intuitively that a large cluster is more general and more loose. Okay, and we usually assume that a given clustering method is monotonic. What that means is that the similarity is decreasing in each step here, in each iteration. So the coherency of our clusters will decline as we keep merging more and more clusters. So if you look at the dendrogram here, the expectation is that this would be the first cluster that we merged, right? B and D. Then we merge G and E, then we merge this cluster with H, and we see that in each step the merge corresponds to a point on the y-axis that shows that the similarity of the two clusters that we merged has gone down compared to the previous iteration. And that holds true for single linkage and complete linkage and average linkage, the linkage criterions we've talked about so far. Okay, but it turns out that does not hold for this centroid measure for computing the similarity of two clusters. So centroid linkage is what we call non-monotonic. And here we've sort of visualized what this means in practice. So we mean that in our dendrogram we get these crossing lines where the given merge is now has been done at a sort of higher degree of similarity than the previous merge in the clustering. So these crossing lines here with circles around them in the dendrogram here corresponds to what we would call inversions. So sort of breaks with this intuitive assumption that we have when we do clustering that for each merge we end up with a more general, less coherent cluster. Okay, so the lesson is that sort of centroid clustering or centroid linkage might seem like the most sort of intuitive and straightforward measure to use, but it has some rather non-intuitive effects on the clusters that are found. Okay, so these are the sort of the four similarity measures that I wanted to mention. One thing to note is that they're all defined sort of on the basis of the pairwise similarities of individual objects that are to be clustered, right? So in practice, that means that the input to a clustering method isn't actually the input to any of these bottom-up clustering methods. Isn't the actual objects themselves, but typically rather a proximity matrix computed for these objects prior to clustering. So that's one of the things you've been asked to do in the latest assignment, right? Is to compute the proximity matrix for the set of vectors, the set of words that you are to represent in your vector space. Where, so for m objects, sort of conceptually, the proximity matrix is an m by m matrix, where each element encodes sort of the similarity between two objects in our collection. And this matrix of pairwise similarities is sort of all we actually need in order to define these single link, complete link, average link, and centroid link measures. We don't need to, in every iteration, recompute all these pairwise distances between the individual objects in our collection, right? It's much more efficient if we just do that once and pass in the proximity matrix as input to the algorithm. Okay, some more details about the tree structure that we end up with. Okay, so far we've talked about how to produce this structure and some properties that this structure might have. But now, once the clustering is complete and we have this, then okay, what do we really have? What can we do with this? And the important thing to note is that we don't really at this point have a single clustering of our data like we did after applying k-means clustering, for example. Because what we have now is actually a set of clusterings. So we have the set of clusters that we started out with, right, when every object is its own cluster. Then we have another set of clusters where B and D, those two singleton clusters, have been replaced with another cluster with those two guys merged. Then we have another set of clusters where we've performed another merge and so on. So each sort of branch in the tree here corresponds to another way of clustering the data, another partition. So we have, in a sense, a set of nested partitions represented by this tree diagram. But in practice, we typically would like to have actually a flat clustering. We would like to be able to say that these 5 clusters or these 5,000 clusters are our clusters, our classes, our groups, rather than working with this entire tree structure. So in practice, what's typically done is that we need to define some way of cutting this tree to obtain a set of flat clusters. So we could define several different sort of criterions for doing this cutting. We could say that we only want to accept clusters that have been merged under for some given threshold for the similarity measure, for example. So say that any clusters that have a similarity score lower than 0.4 or 0.5 or what have you should be discarded. Only the clusters, only the root nodes in the structure below that threshold corresponds to our final clusters. Or we could, like we do for k-means, just specify in advance some number k of the clusters we want to find and say that, okay, once we have a number of, or k number of root nodes in our structure, then we're happy, then we stop clustering. Rather than having an absolute value for where to cut the tree in terms of the similarity score, we could have sort of a relative threshold saying that the drop in the similarity score from one merge to the other needs to be below some threshold. So various ways of doing this, but the point is that it's just important to realize that we don't at the end of performing sort of bottom-up hierarchical clustering, we don't have one unique partitioning of the data without doing something more to the tree structure first. Okay, so this is actually my final slide, the one quick slide on top-down methods, top-down clustering, which is not used nearly as much as bottom-up clustering in practice. So the idea here is to build a tree starting in the opposite direction of bottom-up clustering. Non-surprisingly, given the name. So the starting point is that we consider all objects to form part of the same large cluster. And then we try to define some criterion for splitting that cluster into two. And then iteratively, we keep splitting that cluster, each of those clusters into smaller subgroups, and keep splitting those again until we reach what would correspond to the bottom of our dendrogram with all objects in their own singleton clusters. And the way that split in each step is performed is typically by actually applying a flat clustering algorithm. So we could, for example, apply k-means here for k equals 2. So the flat clustering method we talked about in the previous lecture. We could apply that once, we get 2 clusters, and then we apply k-means with k equals 2 again for each of those clusters, and so on, and keep on applying k-means until we've split all the different groups down to the individual objects. Okay, so a very different way of defining that same structure. So they're typically found to be more efficient than the bottom-up methods, given that flat methods are themselves typically very effective. So k-means it's linear, while these different linkage criterions are typically more complex, with single-linkage being the most efficient one, given this property of being best merge persistent. So that's quadratic complexity. But again, that flat method would need to be applied in for every iteration. That's basically all I wanted to say about hierarchical clustering. One important thing to note, like I briefly mentioned at the beginning, was the importance of the features in all of this. So now we talked about that's what we started talking about when we started talking about vector space representations in the first place, right? We talked about different ways to define contexts, bag of words models versus using n-grams versus looking at features that are based on grammatical relations, for example, or using various types of class-based features. But after that, we haven't really talked about sort of what the features are. If we've just taken those for granted, we have some kind of vector representation, and now let's apply some classification algorithm, or let's apply some clustering algorithm. But I mean, it's just important to remember that what we get out of these methods, supervised or unsupervised, will always depend on the quality of the features that we ourselves designed for representing our data in the first place, right? Because if our features were uninformative, then no matter how complex or intricate our clustering algorithm is, it won't be able to find a sensible structure for us in the data, because the features ultimately are what decides whether the similarity computations that we perform make any sense, right? So it's just important to always bear that in mind, that that's sort of the foundation for how all of these methods work. Do you want to take over before the break, Stefan, or take an early break and start again early? Mm.
So I think it would be natural to take a break now and then come back here in 15 minutes. So that would be, will you work it out? 7 past. And then we'll move on from there.
Yep. See you in 15 minutes.
Okay, welcome back after an early break. Do you hear me okay? Like this? Okay. I'm the other half of your teaching staff this term. I'll be taking over at this point for at least the next 6 or so weeks. So in a sense there's a changing of the guard today, which coincides with a transition in topics. So far in the past 3 lectures, Erik has introduced you to what we call point-wise classification, one classification decision sort of independently of, well, one decision at a time. And the focus has been on geometric models, the vector space metaphor. And we'll now be moving towards, well, in a sense, more complex, structured classification contexts. That is, in a sense, a set of decisions taken jointly, or an interacting set of decisions, and we'll be moving from the geometric perspective to a probabilistic perspective. And hence today I'll introduce you to the very basic building blocks of probability theory, which I hope are largely familiar to you. So that's, I hope, mostly a refresher. We won't do justice to probability theory. We'll just introduce as much as we'll actually need. And then when Erik indicated that he would actually stop a little earlier, I added another set of slides, which are not yet posted on the course page. And I'll probably start with the first application of probabilistic approaches to structured classification. So changing of the guard. The structures that we'll consider will be sequences initially, then sequences where each element in the sequence has some category, a label, and then trees, hierarchically structured objects. And sort of, so you know where we come from. The changing of the guard also coincides with me returning gradually from parental leave. My son is just a little older than Erik's daughter. My second son is just a little older than Erik's daughter. And Erik, towards the end of the semester, will then go out on parental leave, and sort of around the exam time, we'll actually have to learn to make do without Erik, because Guru then will be seeing a lot more of him. So in case we sort of appear tired some days, these may be part of the reason for that. The sort of outlook, 7 more lectures at the end of the semester. We want you to be able to determine for, say, strings, that is sequences of words, like how to recognize speech, or how to recognize speech. That may sound an implausible proposition to you, but in Denmark, I recall that in southern Denmark there was a problem of a motorcycle gang who didn't want the tourists in their sort of area, and hence they at night went out and wrecked those nice beaches. And if you accept, if you allow yourself to believe in that story that I just made up, then that is also a possible utterance of English. How to, next week we have to go out and wreck nice beaches again. And do we have any native speakers of English? No. How to recognize speech, how to recognize speech. They're pretty similar, and the speech recognizer approaches this choice by judging the probability of one string versus the probability of another string. And we would expect that the first one is just a lot more probable, it's more likely. And we'll possibly still at the end of today's session learn how to actually compute these probabilities. From there we'll move to sequences where each element in the sequence bears a label, a category. Here we're using again a sequence of words from the classic time flies like an arrow. And we could imagine that we assign the, so these are parts of speech, as we'll call them, noun, verb, determiner, noun. That's actually the unlikely. So verb, preposition, determiner, noun. That's time flies like an arrow. In the same manner it flies, that is, is engaged in the activity of flying as arrows do. There's the Groucho Marx, I think, pun on this proverb, time flies like an arrow and fruit flies like bananas. And so what he does there is he shifts our expectations about the category assignments, because fruit flies like bananas. He now wants us to look at time flies as a type of insect. So there the flies actually would be a noun. And like as a verb actually, the time flies have a positive attitude. They like arrows. So the disambiguation, the choice between the two interpretations here hinges on the assignment of lexical categories. And we'll learn how to assign these categories to sequences of words. So here we're beginning to do what we'll call syntactic analysis. Essentially, to compute part of what the grammar of the language tells us about the space of interpretations. And we'll push that even further then. I ate sushi with tuna has two possible interpretations. The plausible one is there was tuna among my sushi bites. But I might also have eaten some sushi, vegetarian sushi maybe even, in the company of tuna fish. And so the two interpretations, or the sort of paraphrase would be changing out some of the words. I ate sushi with a fork. So there the fork is clearly not attached to the sushi. It's attached, it somehow tells me something more about the eating. As would be the case in the structure where the with tuna actually is grouped together with the eating, not with the sushi. And I could possibly interpret that as eating in the company of sushi. So these are the structures that we'll compute towards the end of the series. And here the problem that we'll compute is what we call statistical parsing. In sort of broader machine learning terminology, it's structured prediction. We're looking for the most likely, the most probable tree that we can assign to a sequence of things, observable things. In our case, again, linguistic units, words. In all three problems that we'll learn to compute, there's this notion of most likely, and that's what we will approach in terms of probability. So hence, a brief refresher of basics of probability theory. We'll often assume that we're conducting an experiment or a trial, and that there is some process, a random process that we are observing. We'll identify, refer to the space of possible things that can happen, the outcomes, as the sample space. And we will often be interested in some subset of the possible outcomes, and we'll want to say something about their probability. So, for example, our experiment could be rolling a die, and the sample space obviously is the 6 different outcomes. And we might say, what I want to compute is the probability of rolling a 6. So I'll call that event A, and then I can write the probability of A P of A, and that's going to be a real number between 0 and 1 inclusive. Something with probability 0 never happens. Something that with probability 1 always happens is a certainty. But I can define arbitrary events. So I could also say my event, I'll call it B, is getting an even number, and now there are 3 different outcomes that all satisfy that condition. So the definition of the events essentially in proportion to the sample space tells us something about the probability. What's the probability of rolling a 6? That's 1/6. 1 over 6, 0.166, and so on. And we can compute that by the cardinality of the size of the event set, the subset, in proportion to the size of the sample space. So 1 over 6. Hence the probability of getting an even number is going to be half. Every other, well, half the outcomes are even numbers. 2 more examples. I could say my experiment is actually flipping 2 coins, and each coin has 2 outcomes, head or tails, head or tail, I'm never quite sure. And when I have 2 coins that are flipped, then I can get 4 different combinations. 2 heads, 1 head, 1 tail. Here we're assuming that the order actually does matter. So flipping a head and then a tail, or a tail and then a head, are 2 different outcomes. And now I can talk about, say, getting the same outcome twice, 2 heads or 2 tails. That's going to be probability of 0.5, 2 over 4. Or the probability of at least 1 head, and now there are 3 outcomes that actually have that property. The first being a head, the second being a head, or both being a head, and that will have a high probability of 75% or 0.75. We said it's a real number, so we'll actually not say percent, but it translates, of course, directly into times 100, a probability we can look at as a percentage. Finally, rolling 2 dice. What's the size of my sample space? I should have warned you. My approach to teaching is maybe slightly more question-oriented. And a great way of you to make the lecture flow is to just answer these questions. I can be stubborn. So a great way to stall is to refuse to answer my questions, even when they're obvious. I would like to think this is relatively obvious. The size of the sample space when rolling 2 dice. 56. How do you arrive at that number?
It's like when you go from like page 2 to page 3, it's actually 2 pages even though 1 and 2 is multiple in a way. So just like go 6 minus 11 and so on.
I think I kind of followed your reasoning. Are there other opinions? How do you arrive at that number? We know that. So you say there are 6 outcomes for each of the 2 parts, and I multiply them. Rolling 2 dice.
Okay, because I thought like what's the sample size, the sample space size? How many elements there are? Sorry, I think I understood that.
That is actually the question I'm asking, and I think it's the question that Elena is answering, isn't it? How many different outcomes? That's the size of the sample space. And so that's the combinatorics of 6 different outcomes, each followed by another 6 different outcomes. Well, are there more opinions? I'm just the moderator of this discussion here. We have 2 proposals, 36, 6 times 6. You side with Elena. I do too. It's basic combinatorics, but I think we can note that intuitions often fail us when we when we do probabilities, and we kind of I've experienced myself. We feel we have intuitions, but often these are misleading. I'll give you more examples of that, and hence my recommendation is to always reason and calculate. But of course that requires that we choose the right line of reasoning. All right, so here I've again picked various events that I might find relevant, and now that we know the size of the sample space, we can just count the size of the event subset and assign a probability to each of these events. So these are basic probabilities. Often we'll be interested in the probability of multiple events in different configurations. The most basic is what we'll call joint probability, the probability of P, the probability P of A and B. That is the probability that both A and B happen, which we either can write as a comma or as a set intersection here, because in as much as we can gain intuitions about probabilities, I think it's through Venn diagrams. So here the entire slide is the sample, the sample space omega, and each event is a subset, and the probability, the joint probability of A and B is the intersection of these two subsets, hence this set-oriented notation. So for example, when throwing two fair dice, that is where the probability of each outcome is 1/6, we might say we define an event A as the results of the two throws sum to 6, and B as at least one of them is a 1, and I think we had the results sum to 6 here. And now B further selects from that subset, and so we're left with a set of 1 followed by 5 or 5 followed by 1, a subset, the intersection here of 2, and hence the probability, the joint probability of A and B will be 2/36. Here we calculated the individual. I'll actually come back to this calculation. So these are the individual probabilities for A by itself and B by itself. And I just computed the joint probability by effectively defining an event A and B where the set of the subset of outcomes was of cardinality 2/36. Joint probability is the most basic combination of probabilities. Often in a given situation we know something about a situation, and we would expect that to tell us, to help us adjust our probabilities. So we'll write that as A given B using a vertical bar, for example, we might say, what's the probability that the results sum to 6 given or assuming that at least one result is a 1. In the Venn diagrams, that takes us from joint probability over here to conditional probability over here. Essentially now we know that we're inside of the B circle, and we're asking, given that we know that B is true, what's the probability of actually landing in the intersection? So that's generally going to be a higher probability. So knowing that B holds true adjusts our expectation as to A happening given B. So we can express that as, again, the proportion of the intersection to the the space from which we come or select. And now that's no longer omega, that's no longer the sample space, but it's the circle that corresponds to the probability of B, and hence we divide the joint probability by the probability of B, assuming that B has a non-zero probability to make that well defined. From these basic definitions, we can derive some useful rules of calculation, let's say. And the first thing is that we can observe that there is a symmetry in explaining the joint probability of A and B as the probability of A times the probability of B given A. So A and B are going to be true at the same probability as A being true and B being true given A. Or alternatively, probability of B times the probability of A given B. And from these, I can essentially generalize, so that's often called the multiplication rule, what we have here. I can generalize that to any sequence of events, A1 to AN, and compute the joint probability as a iterative application of the multiplication rule called the chain rule, where I say the joint probability of A1 to AN is the probability of A1. I do the same, I apply the same transformation as I do up here repeatedly. Probability of A1 happening, then the probability of A2 happening given A1, the probability of A3 happening given A1 and A2, and so on, until the probability of AN given AN minus 1 to A1. So that's the chain rule, and that's a procedure, a recipe for computation that we'll apply frequently. Right, it's going to be useful to us through the semester because we can break down a seemingly complicated situation here. Joint probability of A1 to AN, we break that down into smaller situations, and we actually will have some flexibility in choosing the breakdown. I sort of delayed computing the probability of, what was it? 2 throws of a die summing to 6, and one of them being a 1, I think, because we hadn't introduced the notion of independence or conditional independence. Intuitively, when I throw 2 dice, the result of the second throw does not depend on the result of the first throw. We're tempted to think that if once I've thrown, so I'm trying to throw a 6 and I've thrown 4 ones, then I'm tempted to throw that the next throw will be something that is not a 1. And that's actually probable, but there's no dependence. The 5th throw is completely unaffected by whatever has been thrown before. So there is throwing dice is a prime example of events that are conditionally independent. So knowing that B is true has no effect on A. And when that is the case, then A and B we call independent of each other. And for 2 events A and B that are independent, the probability of A equals the conditional probability of A given B. Because B's truth value has no bearing on whether or not A comes true. The same goes the other direction. And for 2 conditionally independent events, the joint probability I can compute as the product of the individual probabilities. So the multiplication rule, the chain rule, applies to sequences of events that are not independent. Once I know or assume independence, I can simplify that. I just multiply the probabilities of the individual events. So if we go back to I think this is the example where I promised we'd come back. So the results sum to 6, that's 5 over 36. at least one result is a 1. That's 11 over 36. When we first saw this, I derived the joint probability by picking the subset of, what's our B? At least one result is a 1. So I picked the subset from A where at least one is a 1, 1, 5, or 5, 1. Said observed that's a subset of 2 over 36. So that's the probability of the joint probability of summing two throws to 6 and having at least one of them being a 1. Since we know that these two are the two throws, that is A and B in this case, are conditionally independent, we can just multiply and without doing the math here, I promise you that that will come to the same probability. So, well, that can be your take-home, your exercise on the way back home. So, originally, I, in a sense, constructed an event A prime or C for the conjunction of A and B. And now, with the notion of conditional independence and the knowledge, the understanding that the joint probability of two independent events is the product of the probabilities of the individual events, we have an alternative way of calculating that. Let's apply, so that was essentially the refresher of basics of probability theory. Scratching the surface, some might say, if any of you have a background in mathematical statistics, then this is very basic. But that will be sufficient for our purposes, because we'll solve specific machine learning problems in the natural language analysis space. I have one example that I wanted to work through with you. A classic again. You'll find it on many. In fact, I think I'll link from the course page, in addition to the slides, online tutorial on probability basics, and that actually goes through the same example, so you'll recognize it there. So let's say we have a rare disease, whatever, cancer. No, we don't have good tests for cancer. Well, we do for some, I think. And so some rare disease and test that is pretty accurate, but not perfect. So the disease, often called the prevalence in medical terms, means that 1 in 1,000 people suffer from this disease. So that gives it a probability of 1 over 1,000, a very small probability, 0.0001. For the test, we know that it has a false negative rate of 1% and a false positive rate of 2%. False negative, false positive, you've heard before. And these are very closely related usages here. So what does it mean for a medical test to give a false negative? Intuitions? But the test is false. And the false positive is the inverse. So the test says you're sick, but actually you're not. And that's, I think, a very common situation, that you have pretty accurate tests, but they're not perfect. And hence, Yoda, or friend Yoda, has taken the test, the result is positive, and now he's turning to us and saying, gosh, the test is so good, I reckon I'm probably sick. And we'll try to work out what's the probability that Yoda actually has the disease. And do you, sort of thinking about this problem, maybe putting yourself into Yoda's shoes, do you see how in making that judgment, it's important to take into consideration the probability of the disease, how many people actually get the disease. The disease is not very common after all. And the accuracy or the reliability of the test. So how can we compute that? Let's try to translate into P's, into probability expressions. We'll say event A is having the disease and event B is testing positively. And that means we know some things. We just translate the information I gave you on the preceding slide into probability of the disease is 0.001. It's not very common, 1 in 1,000. The probability of testing positive given the disease, so that's the reliability of the test, that's the inverse of the false negative rate, is 0.99. Sorry, did I say having the disease? So the you test positively given that you have the disease in 99% of all cases, 99 of 100 cases. 1 in 100 who actually has the disease will not test positive. And the false positive rate, you're actually not sick, not A, but test positive in 2 out of 100 cases. What we want is, what Yoda wants to know really is the probability of actually being sick given that he has tested positively. We know that B is true and we want to know what's the probability of A being true. We'll approach that in a probability table for the individual probabilities and the joint probabilities. And we can fill in the things that we know. We know the probability of the disease. And in a probability table like this, we'll want the sum over all possible. So each cell here will be the joint probability of B and A, or the joint probability of B and not A, not B and A, not B, not A. And the sum over all of these will want to be 1. It's got to be one of these 4, is what this means. And so from this, we can easily derive the probability of not being sick. That's most people, 999 out of 1,000. And we can further fill in the joint probability of A and B by using the multiplication rule. We know P of A and we know P of B given A. So we just multiply. We can do the same thing for not A, because we know P of not A and we know P of B, and P of B. Sorry, we know the probability P of not A here, and the probability of B given not A. That is testing positive but actually not being sick. The false positive rate of the test. Now we can just sum in the row and fill in the missing values here such that the column sums come out right. And we have a complete probability table for the 4 different joint probabilities in this scenario. And from these, we can now compute what we actually want, namely the conditional probability of being sick given a positive test using the equation that the definition of conditional probability. That's the intersection of A and B in the Venn circle diagram in proportion to the B circle. And we can read these off the table now and find that Yoda actually has a comparatively low probability, less than 5%, of actually being sick. So we can hopefully put his mind, if not at perfect peace, then he should be far less alarmed now than he maybe was earlier. And most people, I think, find this much lower than intuitions would lead us to expect. And that's in no small part related to the small probability of actually having the disease. Yes?
But since there's nothing special about Yola, can we just say this person tested positive and you don't have to worry? You can say this to basically anyone who tested positive, right?
Yes. Well, 5% of having cancer is maybe not quite not having to worry. Well, so now we're trying to excuse me? Okay, I know nothing about the actual reliability, but you do? But that's certainly a possible interpretation of our finding here, that the test here doesn't tell us enough, let's say. It certainly tells us something, because Yoda now knows that his probability of having the disease is much higher than 1 over 1,000. So, I mean, we don't worry about being the 1 in 1,000. But Yoda might worry being one of the 5 in 100. And hence, that might call for follow-up diagnostics, I imagine. Yes? So exactly, I was going to say. So if this is a very cheap first screening test, then it could actually be quite useful. Because now we know, okay, Yoda maybe should actually proceed to further diagnostics. So let's leave the, I mean, I think what we're seeing is that these considerations are actually important in, well, making medical decisions, but also making policy decisions about, or strategy decisions about diagnostics and treatment. And our sort of take-home observation here is that I remember when I first sort of worked through this, I felt, no, that's certainly not what my intuition would have led me to expect. That's why I picked this example. So that was essentially deriving conditional probability from so what we wanted was the conditional probability of A given B, having the disease given a positive test. What we knew was the probability of testing positively given the disease or not having the disease. So we knew the inverse conditional probabilities to those that Yoda actually really wanted to know. And through filling in the missing joint probabilities, we could then derive that conditional probability. Effectively, what we just did could be considered an application of what's known as Bayes' theorem. And Bayes' theorem really is a basic observation from these equations here. So here we broke down the joint probability into either P of A and well, times P of B given A, or the inverse. Now I can take the two right-hand sides of this equation, so this term and this term are equal, and I can divide by either P of A or P of B and put one of the two conditional probabilities as a term in its own right on one of the sides of the equation. So that gives me an equation that allows me to compute one conditional probability in terms of the other conditional probability and the probabilities of the two basic events. And that is the essence of Bayes' theorem, where we have just applied this transformation. We've divided by P of B, the two sides of that equation from the multiplication rule. And that gives us that a way to compute P of A given B from P of B given A times P of A in proportion to P of B. And I think if you sit back and think a little about that, I actually find that reasonably intuitive. And base rule is just a practical way of shifting around conditional probabilities. It reverses the order of dependence, which can be useful. We've just seen that in our example. It allows us to compute one conditional probability, even though maybe what we know on the outside is the inverse conditional probability. And in conjunction with the chain rule, we'll often use Bayes' theorem to compute the probabilities that we actually want from the probabilities that we can know based on on things we can observe. Finally, this is the last missing piece in the basics of probability theory. Two axioms: the sum, or the probability of all possible outcomes is going to be 1. So the probability of anything from the sample space, whatever, is a certainty. It's going to be one of them. And the probability of A is 1 minus the probability of not A. Again, you could draw the Venn diagrams and easily derive that. So the sum of the probability of A or not A is going to be 1. That's a certainty. And hence it follows, so I can just transform that equation and derive this one. All right, I was going to sort of send you home with the Monty Hall problem. It's again on the in the space of testing our intuitions. So let me very briefly walk you through it, and then we'll actually use it as our welcome back. Here is what happened last week problem next week. So assume there's a game show with 3 doors, hidden doors. And behind 2 of them there's a goat, and behind the 3rd door there's a car. Assume further you're more interested in the car than the goats. May depend on your profession. But we assume the car is more valuable even than the goats. And the rules of the game are that the contestant, the player, selects a door that she hopes has the car behind it. What's the probability of picking a door with the car? That's going to be 1/3. But now the twist is, before she actually gets to open that door, the game show host opens one of the other doors and reveals a goat. And the question is, should the contestant now stick to her original choice? Or should she actually switch to the other unopened door? So has knowing that there is a goat behind one of the other 2 doors changed anything about the probability of getting the car behind the original door or the remaining 3rd door? What should she do? So coming up somewhere between next week and today, I think I'll actually start on the language models. These are the extra slides that I added during the first half. We'll now apply probability theory to sequences of things, in our case words. And again, it's very intuitive that in a given context, there's a limited range of choices that I can put into that box. Do you want to come to the movies? And, well, I'll leave it to your imagination. What? Eat popcorn, probably. Det var en... Je ne parle... That has to be français. Has to be... No E? Right. Okay. I'll try to find someone who can help me fix that. Maybe you could email me. I don't speak any French. And so what we observe here is that natural language, sort of by design, contains some redundancy. which makes it robust in communication. And in part, taking advantage of that redundancy, there is a certain level of predictability. And in all of these examples, I want you to sense, to observe that the previous context constrains what can go into these slots. And ultimately, those constraints are going to be in terms of semantics, meaning, and syntax, grammar. But we'll approach them in a much more mundane manner. We'll approach them by frequency, by probability. So we'll observe that certain words tend to follow certain words, and we'll just make that precise. I'll skip this part. So we're moving into this section, which string is most likely. And the tool, the probabilistic model that we'll apply to this problem is called a language model. And the language model M gives us a probability, P of M, for a string X, a sequence of words, in some language L. L here is the sample space, the set of all possible strings that for most natural languages need not be finite. The probability is going to be a true probability between 1 and 0, and the sum over all possible, the sum of probabilities over all possible strings is going to add to 1. These are just the axioms of basic probability theories. Language models are incredibly useful. You pick up your cell phone, you're bound to probably use multiple, or you certainly use language models in more than one type of interaction with your cell phone. Machine translation, speech recognition, spell checkers, input prediction, predicting the next word. Even though they're sort of the most basic probabilistic sequence model, they have had an important part, I would say, in making language technologies everyday useful technologies. We'll now just essentially fill in the terms from our language modeling problem into the equations that we defined earlier. So we'll say X is a sequence of words W1 to Wn. We can call that a sequence of events, the event of putting W1 into the first position of a sentence, and so on. And we'll use the chain rule to compute the probability of the string, the sentence as a whole, as the probability of the individual words at the context where they occur. So conditioned on the string up to that point. For example, if I wanted to estimate or assign a probability to I want to go to the beach, that would sort of boil down into a chain of products of conditional probabilities like the one down here. Looking at this, you might already wonder, how am I going to know the probability of 2 given the preceding 4 words I want to go? That might still seem a reasonably plausible thing to happen, but the longer the context, the harder it's going to be to actually assign a probability to a word in that context. So that has to do with data sparseness. There are certainly I'll come back to data sparseness. To make that easier to compute and those probabilities easier and more reliable to actually estimate, we'll make a simplifying assumption. In a sense, an assumption of partial independence, which is called the Markov assumption. And the Markov assumption essentially says the conditions on what can go into position n depend mostly on the most immediately preceding context. Maybe just one word to the left, maybe two words to the left. Some limited number of words to the left, some window. I don't want to have to deal with. So in a 20-word sentence, the probability of the 18th word will depend much more strongly on the 17th and maybe the 16th word than on the first word. That makes good sense. So that's the Markov assumption, where we'll say the immediately preceding n-1 elements approximate the conditioning effect of the full sequence. These are the ones that I'll take into consideration. Instead of beach, I want to go to the. If we say we'll only look at windows of 3 words, then the context will be the immediately preceding 2 words. A sequence of 3 words we'll call an n-gram for n equals 3, a trigram. And in what we'll be doing, we'll be mostly sticking to bigrams even, just one preceding words, n equals 2. In, say, the Google machine translation system, Google last I knew, a couple of years ago in fact, Google was using n-grams for n up to 7, which they compute over essentially the complete crawl of the web text for a given language. And that gives Google very powerful, somewhat storage intensive handle on assigning probabilities to strings. So you can immediately see, of course, the larger n, the more different combinations for which I need to keep track of probabilities and that I need to look up and multiply together. So narrowing the window makes the computation cheaper, makes the model smaller, but loses, of course, a little bit of the predictive power of the preceding context. So one word, just the immediately preceding word, is clearly the most important, but it's not hard to see that a little further to the left of the current word, there can also be useful information that a bigram n equals 2 model will not capture. Right, so here we have that. Bigrams, I want 1, 2 to go. These are the units of probability computation, or trigrams or 4grams. And I think I'll drop here and next week actually give you the what remains of the formal definition of the n-gram models, the recipe to assign probabilities, to estimate these probabilities, and a few more reflections on the problem of data sparsity. Okay, leave here. Slides that are currently on the website don't have the past 5 or so slides on n-grams. I'll update I'll post these in the course of the afternoon. So please go and refresh that PDF that is currently on the web page. Thank you.